Welcome to the deep dive. We're jumping straight into the static, that fascinating world of electrical charges just sitting there, the kind that makes your hair stand on end sometimes. It's easy to think of electricity as, well, the current powering our gadgets.
Right, the stuff flowing through wires.
But this whole story really started with charges that weren't going anywhere.
It did indeed. And it's pretty amazing how far back people notice this stuff. The word electricity itself comes from the Greek electron.
Electron, meaning amber.
Exactly, amber, that fossilized tree resin.
Okay, so what's the deal with amber?
Well, way back around 600 BC, there was this Greek philosopher, Thales of Miletus. And he noticed that if he rubbed amber with wool, it suddenly got this weird ability to attract light things, bits of paper, dust, that sort of stuff.
Just by rubbing it. A bit mysterious.
Very mysterious back then. A real head scratcher. And it took ages to figure out.
Yeah, it wasn't like they understood it overnight, right?
Not at all. We're talking nearly 2,000 years before someone really started to get a handle on it. William Gilbert, around 1600 AD.
Wow.
Yeah, he started putting together actual theories about why rubbing amber did that.
Yeah.
So from those ancient observations to, the beginnings of modern electrical ideas, that's where our deep dive starts. We're using the sources you provided.
Right.
And our mission, really, is to unpack the main ideas, look at some, frankly, surprising phenomena, and figure out why this static stuff actually matters to you.
All right, charge is at rest. Let's try to picture it. Imagine a regular plastic comb.
Okay.
Hold it near some tiny paper pieces, nothing happens, but run it through your dry hair a few times.
And suddenly it snatches them up.
Exactly, that rubbing action is key.
It really is a trigger.
Yeah.
And you see the same thing with, say, a glass rod and a piece of silk. Before you rub them, they're just a rod and a cloth.
Nothing special.
Right. But rub them together, and suddenly both the glass and the silk can pick up those little paper bits.
And the classic party trick, the balloon.
Oh.
Blow up a balloon, try to stick it to the wall, falls right down.
Yep.
But give it a good rub on your jumper, maybe some wool.
And bam, it sticks to the wall.
Sticks right there. But then, here's the interesting bit. Rub two balloons the same way and try to bring them close together.
They push each other away.
They really do. It's like they've developed this, I don't know, invisible force field.
That invisible push or pull. That's what we call the electrostatic force. It's the force that shows up because of the rubbing, making the objects electrically charged.
Electrically charged.
And the key thing, like you said, is that this is static electricity. The charge isn't flowing anywhere, like in a wire. It's built up and staying put on the comb, or the balloon, or the glass.
So we've got these charged bodies, and then everything else is what? Uncharged? Or neutral?
Uncharged or neutral, exactly. And what's interesting is that a charged object can actually pull on something that isn't charged.
Like the balloon pulling on the neutral wall?
Precisely. The wall itself wasn't rubbed, wasn't charged up, but it was still attracted to the charged balloon. Now here's an important point, though. You mostly see these strong static effects with insulators.
Materials that don't let charge move easily?
Right. Insulators, or sometimes conductors, that are completely isolated, like not touching anything that will let the charge drain away. And this all leads to that fundamental rule.
Let me guess. Opposites attract. Likes repel.
You got it. Like charges push each other away, and unlike charges pull together. That's really the bedrock principle here.
But this isn't just lab experiments or party tricks, is it? We bump into this stuff all the time.
Oh, absolutely.
Like when you comb dry hair, you sometimes hear that little crackling sound.
Uh-huh. And your hair might even lift up towards the comb?
Yeah. Or dust sticking to a mirror right after you wiped it with a dry cloth. It drives me nuts.
Happens all the time. Or even, if you get close to an old TV screen just after you turn it off, sometimes the little hairs on your arm stand up.
Yeah, I felt that. Creepy.
All static electricity. Just everyday examples.
Okay, so rubbing makes things charged, but what's really going on, like down at the atomic level? Let's get into the modern theory.
Right, the electronic theory. It all comes down to the atom, the basic building block of everything.
Protons, neutrons, electrons, right?
That's them. Protons have a positive charge, electrons have a negative charge, and neutrons are, well, neutral, no charge. And here's the crucial bit. The positive charge on a proton is exactly the same size as the negative charge on an electron, just opposite.
Like a perfect balance.
A perfect balance. Now think about how they're arranged. The protons and neutrons are packed together in the middle, the nucleus.
Okay.
And the electrons. They're whizzing around the nucleus in different layers or shells.
Mm-hmm.
The ones in the outermost shell are called valence electrons. They're pretty important.
Valence electrons.
And sometimes you even have electrons that are even more loosely held, kind of beyond that outer shell. We call those free electrons.
Free electrons. Sounds like they might be the ones doing the moving.
Bingo. They are absolutely the key players because it's the transfer of these electrons specifically, these more loosely held ones, that makes objects charged.
So a normal atom is neutral, equal protons and electrons.
Exactly. The positive protons perfectly balance the negative electrons. No overall charge.
But if that balance gets upset...
Well, if an atom grabs an extra electron, suddenly it has more negative than positive. It becomes negatively charged.
Makes sense.
And conversely, if an atom loses an electron, it's left with more positive protons than negative electrons. So it ends up with a net positive charge.
So it's all about gaining or losing electrons.
That's the essence of it.
Mm-hmm.
And these charged particles, atoms, or even whole objects, they exert forces on each other through their electric fields. It's like an invisible influence spreading out from them.
They don't even need to touch?
Nope, they can attract or repel across a distance.
Okay, so back to the rubbing. The glass rod and the silk. What's happening with the electrons there?
Okay, so when you rub them, it really depends on how tightly each material holds onto its electrons. For glass and silk, well, the electrons in the glass atoms are actually held a bit less tightly than the ones in the silk.
Less tightly in the glass.
Right. So the friction, the rubbing energy, gives some of those outer electrons in the glass enough oomph to jump over to the silk.
So the glass loses electrons, making it positive.
Exactly. It ends up with a deficit of electrons, so net positive charge. And the silk, it gained those electrons.
So it becomes negative.
It has a surplus of electrons, net negative charge, simple transfer.
Okay, glass positive, silk negative. Got it. What about the other example, ebonite? That hard rubbery stuff and fur.
Similar idea, electron transfer, but the roles are reversed. In this case, the fur holds onto its outermost electrons less tightly than the ebonite does.
Ah, so this time the fur loses electrons.
Precisely. When you rub them, electrons jump from the fur to the ebonite.
Making the ebonite negative.
Right, it gets an excess of electrons, negative charge, and the fur, having lost electrons, is left with a positive charge.
So which way the electrons jump really depends on the specific materials you're rubbing together.
Absolutely. It's about which material has the looser grip on its electrons.
Okay. Now, we touched on this, but let's really nail down these rules. How charged things interact. The laws.
The fundamental laws of electrostatics, yes. Like, charges repel, unlike charges attract. We can see this really clearly with some classic demos.
Like suspending charged rods.
Exactly. Imagine you hang up a glass rod you've rubbed with silk, so it's positive. Then you bring another positively charged glass rod near it.
They'll push apart, repel.
Right. Positive repels positive. Now do the same thing, but with two ebonite rods rubbed with fur, both negative.
Same thing. They'll repel, negative repels negative.
Perfect. And now for the attraction. Take that suspended positive glass rod and bring near it an ebonite rod you rubbed with fur, so it's negative.
They'll pull towards each other. Opposites attract.
That's it. These simple experiments really drive home that the charge on the ebonite from fur is the opposite of the charge on the glass from silk. And it confirms those laws. Likes repel, unlikes attract.
Okay, clear enough. So charges are made, they interact. But you mentioned earlier that not all materials handle charge the same way. Conductors versus insulators.
A crucial distinction, absolutely. Good conductors are materials that let electric charge flow through them really easily.
Like metals.
Metals are the classic example. Silver, copper, aluminum are excellent. But also things like mercury, the earth itself, even the human body can conduct electricity pretty well.
Okay, so they let charge move. What about the other kinds?
Well, then you have bad conductors.
Yeah.
They resist the flow of charge quite a bit. Most nonmetals are in this group, though there are exceptions, like graphite conducts and tap water can conduct a little.
And then insulators.
Insulators basically block the flow of charge almost completely. Think rubber, glass, plastic, dry air, pure water, wood, sulfur. They hold on to charge, they don't let it move through.
So what's the underlying difference? Why are metals so different from rubber, say?
It all comes back to those free electrons we talked about earlier.
Ah, the loosely bound ones.
Exactly. Good conductors have loads of them. Millions, billions, just free to move around inside the material. They act like a sea of charge carriers.
So they can carry the charge easily?
Right. Bad conductors have far fewer free electrons available. And insulators. They have virtually none that are free to move. The electrons are all tightly bound to their atoms.
Got it. Lots of free electrons means good conductor, very few means insulator. Okay, so we've mostly talked about making static charge by rubbing insulators. How do you actually get charge onto a conductor if it flows so easily?
Good question. There are two main ways: conduction and induction.
Conduction and induction. Let's start with conduction.
Conduction is the direct contact method. You take a conductor that's already charged and you touch it to an uncharged conductor.
Okay, physical touch.
Physical touch. Some of the excess charge from the first object will just flow over onto the second object, sharing the charge between them.
So they both end up with the same type of charge.
Yes. If you touch a negatively charged metal sphere to a neutral one, they both end up negative. It's a direct transfer, a sharing process.
Okay, straightforward. What about induction then? That sounds less direct.
It is. Induction is charging without touching. You bring a charged object near an uncharged conductor, but don't let them make contact.
Just bring it close.
Just bring it close. The electric field of the charged object influences the charges within the uncharged conductor.
How so?
Well, say you bring a positive rod near a neutral metal sphere. The positive rod will attract the free electrons in the metal sphere. So those electrons will move toward the side of the sphere closest to the rod,
Making that side negative.
making that side negative. And because the electrons moved away from the other side of the sphere, that far side is left with a net positive charge.
Ah, so you get a separation of charge within the sphere just because the charged rod is nearby.
Exactly, a temporary separation. Importantly, no charge actually jumped from the rod to the sphere. It's just a rearrangement within the sphere itself.
So let's recap the difference.
Yeah.
Conduction, touch, charge transfers, both get same charge. The first object loses some charge.
Right.
Induction, no touch, charge just rearranges inside the second object. Opposite charge induced nearby, same charge induced further away. No charge transferred overall.
Perfect. And with induction, if you then take the charged rod away,
The charges in the sphere just spread back out and it becomes neutral again.
precisely. The induced charge separation is temporary unless you do something else, like grounding the far side while the rod is still there. But fundamentally, induction is about influence at a distance. Conduction is about transfer through contact.
Okay, these concepts are getting clearer, but how do we actually know if something is charged? Or tell if it's positive or negative? That's where something called an electroscope comes in, doesn't it?
That's exactly its job. An electroscope is a device designed purely to detect if an object has a net electric charge, and sometimes to figure out the sign of that charge, positive or negative.
Are there different kinds?
Two main types you usually encounter. The simpler one is the pickball electroscope, and the more sensitive one is the Gold-Leaf Electroscope.
Pithball. Sounds basic. What's that involve?
It really is basic. It's just a tiny, very lightweight ball, usually made of pith, that's spongy stuff from inside plant stems,
Okay.
hanging from a silk thread attached to an insulating stand. That's it.
So how does that little ball tell you anything?
You just bring the object you're testing near the pick ball, don't touch it. If the object is charged, it will either attract or repel the lightweight pith ball. You'll see the ball move.
Ah, so any movement means the object is charged.
Pretty much. If the object is uncharged, the pith ball will just hang there unaffected.
Okay, so it detects charge. How do you tell positive from negative with it?
For that, you need to first give the pith ball a known charge. Let's say you touch it with a glass rod rubbed with silk. Now the pith ball is positive.
Right.
Then you bring your unknown charged object close. If the pith ball swings away, further repelled.
Means the object is also positive, like charges repel.
Exactly. But if the pith ball swings towards the object,
Then the object must be negative, unlike charges attract.
that's the logic. It's pretty straightforward. There's an activity in the sources using a foil-covered ball, which works the same way.
Okay, simple but effective for basic tests.
Now, the Gold-Leaf Electroscope sounds fancier.
It is a bit more refined and generally more sensitive. Imagine a metal rod, usually brass, going vertically through an insulating plug into a glass jar or case.
To keep drafts out.
Exactly. At the top of the rod, outside the jar, there's a metal disc or knob. And at the bottom end, inside the jar attached to the rod, are two very thin, delicate strips of gold leaf.
Gold leaf, okay. Why gold? It's extremely malleable, so you can make it incredibly thin and light, meaning even a small amount of charge will cause the leaves to move noticeably. Sometimes there's also metal foil inside the jar connected to earth for shielding.
So how does this one detect a charge?
If you touch a charged object to the metal disc on top,
Uh-huh.
the charge travels down the metal rod and spreads onto both gold leaves. Since both leaves get the same type of charge, either both positive or both negative, they repel each other.
Ah, so they spread apart.
They diverge, yes. The amount they spread apart gives you an idea of how much charge there is. If you touch it with an uncharged object, the leaves don't move.
So the leaf divergence is the key signal. Does this help tell conductors from insulators too?
It can, yes. Imagine you have two identical gold-leaf electroscopes. You charge one up so its leaves are diverged.
Okay.
Then you take the object you want to test, say a rod, and use it to bridge the gap, touching the disc of the charged electroscope and the disc of the uncharged one simultaneously. If the leaves on the second electroscope also diverge, it means charge flowed through your test object. So it must be a conductor.
And if second electroscope's leaves do nothing?
Then your object didn't let the charge pass. It's an insulator.
Clever test. And finally, determining the type of charge, positive or negative, with the gold leaf.
It's similar to the pith ball method. First, you give the electroscope a known charge. Let's say you charge it positively, so the leaves are already diverged somewhat.
Okay, leaves are apart, positive charge.
Now, bring the object with the unknown charge near the top disc. Don't touch it this time, just bring it close.
Right, induction effect.
Exactly. If the leaves spread further apart,
More repulsion means the object is also positive.
correct. Adding more like charge increases the repulsion. But if the leaves collapse, come closer together.
That means the object's charge is attracting the charge on the leaves, canceling some of it out, so the object must be negative.
Precisely. The attraction from the nearby negative object draws some positive charge up the rod, reducing the charge on the leaves so they repel less. And it works the other way too if you start with a negatively charged electroscope.
So the electroscope in its forms is a really useful tool for actually investigating this invisible world of static charge.
Absolutely. Fundamental tool in the history of electricity.
Okay, let's shift scale
Yeah.
now, big time. From the
Same.
lab bench to, well, the sky. Atmospheric electricity, lightning.
Oh, yes. The most dramatic display of static electricity there is.
It really is awe-inspiring. And wasn't it Benjamin Franklin who first connected clouds and electricity?
It was his famous and frankly incredibly dangerous kite experiment back in, 1749, during a thunderstorm.
Flying a kite in a storm, what was he thinking?
He was thinking scientifically. He wanted to prove clouds carried electrical charge. And he did. He noticed sparks jumping from a key tied to the kite string to his hand.
Wow, proof positive, I guess. But how do clouds get so charged up in the first place?
It's complex, still debated in some details, but friction is a big part of it. Inside big storm clouds, you have intense movement updrafts, downdrafts, collisions between ice crystals, water droplets, hail.
Rubbing and bumping.
A massive amount. And these collisions can knock electrons off, separating charges. Typically, the bottom of the cloud tends to accumulate a negative charge, while the upper parts become more positive.
So you get these huge regions of separated charge, and lightning is just a giant spark.
Essentially, yes.
Yes.
It's a massive electrical discharge.
Yeah.
When the difference in charge, the electrical potential between two regions, maybe within the same cloud, or between two clouds, or crucially between the cloud and the ground gets large enough, the air, which is normally an insulator, just can't hold it back anymore, it breaks down, and you get this huge rapid flow of charge, the lightning bolt.
And that releases enormous energy.
Huge amounts. That's the bright flash, the intense heat, and the sound, thunder. That's the air around the lightning channel getting heated so rapidly it expands explosively, creating a shock wave.
So a charged cloud overhead can actually affect the ground beneath it.
Definitely. Through induction. If a negatively charged cloud base moves over the ground, it repels negative charges in the earth and attracts positive charges to the surface directly underneath it, especially on tall things.
Like trees, buildings.
Exactly. Tall, pointy things are good at accumulating this induced charge.
Yeah.
And if that charge difference between the cloud and the treetop or building becomes strong enough, zap, cloud-to-ground lightning strike.
Which is obviously incredibly dangerous.
Terribly dangerous. Lightning can start fires. It can literally shatter buildings or trees from the explosive heating of moisture inside them. And of course, it's lethal to people and animals caught in its path.
Yeah, it makes you think twice about standing under a tree in a storm.
Absolutely. Lightning safety is serious. Inside, stay away from plumbing, wires, concrete walls even. Unplug things. Outside, get into a proper building or a car with a metal roof. Avoid open fields, isolated tall objects. If you're truly caught out, crouching low is better than lying flat.
Good advice. Now, to protect buildings, especially tall ones, we use lightning conductors, right? How do those actually work?
Right, lightning rods are conductors. It's a clever system. Typically, you have sharp metal spikes sticking up from the highest point of the building.
The pointy bits on top.
those pointy bits. They're connected by a thick metal cable, usually copper, that runs down the outside of the building,
All the way down.
all the way down, and then it's connected to a big metal plate or grid buried deep in the ground. That connection to the earth is called, well, earthing or grounding.
Okay, spikes, cable, ground connection. How does that stop a massive lightning bolt?
It works mainly through induction and providing an easy path. When a charged storm cloud passes over, the sharp points of the conductor develop a strong opposite induced charge. Remember how charge concentrates at points?
Yeah.
This actually helps to sort of leak charge into the air, neutralizing some of the cloud charge nearby, potentially preventing a strike. But more importantly,
Yes.
if a strike is going to happen, it's much more likely to hit the conductor because it offers the easiest, lowest resistance path for the electricity to follow down to the ground.
So it basically intercepts the strike and channels it safely away from the building itself.
Exactly. The massive current flows harmlessly down the thick cable and dissipates safely into the earth, which can absorb huge amounts of charge. It protects the building from damage.
A pretty vital invention, especially for skyscrapers. Now, it seems counterintuitive, but does lightning actually have any benefits? Aside from the light show.
Surprisingly, yes. It's not all destruction. There's even a theory that early lightning strikes might have been crucial for the origin of life on Earth, providing energy for chemical reaction.
Wow, okay. What about currently?
Two main things. First, nitrogen fixation. Nitrogen gas makes up most of our air, but plants can't use it directly.
Right, they need nitrates and stuff.
Exactly. The incredible energy in a lightning bolt can actually break apart the strong bonds in nitrogen and oxygen, ochre and toluene molecules in the air.
Forces them to react.
Forces them to react, forming nitrogen oxides, which then dissolve in rain to form nitric acid. This falls to the ground, reacts with soil minerals, and boom, you get nitrates. Plant fertilizer made by lightning.
It's nature's own fertilizer factory. That's amazing. What's the other benefit?
Ozone formation. That same intense electrical discharge can also convert some of the normal oxygen, O2 into ozone.
Ozone.
Like the ozone layer.
Precisely. While ozone near the ground isn't great, the ozone layer high up in the stratosphere is vital. It absorbs most of the sun's harmful ultraviolet radiation. Lightning contributes to maintaining that protective layer.
So lightning helps make plant food and protects us from UV rays. Who knew?
It's pretty remarkable, isn't it, how these powerful natural events have these knock-on beneficial effects.
It really is. From Thales rubbing amber and wondering why dust stuck to it, all the way to understanding how lightning works, protecting buildings from it, and even appreciating its role in making the planet habitable. It's quite a journey.
An incredible scientific journey built on observing these fundamental electrical phenomena. Well, we've certainly covered a lot of ground in this deep dive into static electricity. We looked at the basics, how charges are made by rubbing, how they attract and repel.
The difference between conductors and insulators based on those free electrons.
Right, and the ways to charge conductors, conduction by touch, induction from afar. We looked at the electroscope, that clever charge detector.
And then the big stuff, atmospheric electricity, the mechanics of lightning, how to stay safe, and how lightning conductors work.
Plus those surprising upsides like nitrogen fixation and ozone.
Yeah, it really ties together from the microscopic electron transfer to these huge atmospheric events.
What really strikes me is how something that seems so simple, like static cling, connects to these profound processes, protecting buildings, maybe even helping life get started, feeding plants.
It shows how fundamental these electrical forces are.
So here's something to think about as you go about your day. Consider the impact of the seemingly simple thing, static electricity. From those first curious ancient Greek observations to essential modern safety, and maybe even the conditions for life itself, it really makes you wonder, doesn't it? What other basic forces are out there, all around us, holding similar surprising connections, maybe untapped potential we haven't even realized yet?
A fascinating question to ponder.
Definitely something to think about. Thanks for tuning in to this deep dive.